In this video, I'm going to take you through using complex numbers to solve AC circuits. In our previous video, we learned about representation of complex numbers in AC circuits. So we are going to see how we use the complex numbers to solve AC circuit problems. Voltages and currents in AC circuits can be represented as complex numbers. The impedance Z can also be represented as what? A complex number. To represent complex numbers as to represent phases as complex numbers, 1. Resistance always takes a real number, or resistance becomes the real part of our complex number. So if you want to find the impedance and there is resistance, resistance will take the real part of the complex number. Number 2, the inductive reactance. The inductive reactance will take the imaginary part, but it will be positive. So we use positive to represent the inductive reactance when we are representing AC circuits with what? Complex numbers. This is because the the voltage VL always leads the current I by what? 90 degrees. So since it is leading, we use negative here, so we use positive to represent the imaginary part of the complex number as the inductive reactance. Number 3, the capacitive reactance. So a capacitive reactance is represented as pure imaginary number. So this is a pure imaginary number with a negative imaginary part. When we say a pure imaginary number, it means that it doesn't have a real part. Likewise, the inductive reactance, the only difference is that we make it negative operator. It's negative because the current is is leading the voltage rather, or the voltage should lag behind the current by 90 degrees. So that is how we represent our AC circuit. So you know that our resistor is taking real parts, our inductive reactance, let's make it XL, is taking what? Positive J. Then our XC is taking negative J. Now let's take an example and see how we can use it to solve. So you have this. Express in rectangular and polar notations the impedance of each of the following circuits at a frequency of 50 Hz. So we have to express in rectangular and polar notation the impedance of each of the following circuits at a frequency of 50 Hz. The first one is resistance of 20 ohm. The second one is a resistance of 20 ohm in series with an inductance of 0.1 henries. Then the third one is a resistance of 50 ohm in series with a capacitance of 40 microfarad. So we are to express this in what? Complex numbers, the rectangular and polar notations. So let's take the first part A. So the A part is simply what? A resistance of 20 ohm. And you know resistance is taking the raw part. So Z impedance is simply 20 plus what? J0, because the imaginary part is 0 since it's purely real number. All into brackets ohms. And this is how we represent it in the rectangular mode. In the polar mode, we are simply going to have 20 angle 0 degrees, right? So this is a simple notation for the pure resistor, or when resistors are only acting. So now the second part is saying that you have a resistor R equals 20 ohm, then you have our XL, so inductive resistance, but they were given inductance, right? So they give us inductance L. So I have my L to be equal to 0.1 henries. Now, whenever I have L, I need XL. XL is equal to 2 pi F L, right? So 2 pi FL here is simply going to give me 2 times pi times my frequency 50 given by the question times 0.1, and this will surely give me 31.4, so 0.1 henries. So this will cancel and I'm going to have 5, 10. So 10 times 0.14 is 31.4, and it's an inductive reactance, so ohms. So let's see. Once I have this, you know that the inductive reactance is taking positive imaginary part. So I'm going to have the 20 taking the real part plus 31.4 G, right? So this becomes the rectangular part. And now, what will be the polar part? The polar form or polar representation will have the magnitude of this. So I'll have 20 squared. So the magnitude of the impedance becomes 20 squared plus 31.4 squared. And that is going to give me 37.2 ohm. So in my polar form, I have 37.2 ohm. Angle, what will be my angle? Tan inverse of my 31.4, my XL over my R, and my R is 20. So what am I getting for this? So we'll be getting 37.2 here, angle 57.5 degrees. So ohms, and this is in the polar form. This was in the rectangular form. Let's take the last part, C. A resistance R of 50 ohm in series with a capacitor C, capacitance 40 microfarad. In rectangular form, I have this representing the raw part, then I find my XC, which is 1 over 2 pi FC. So 1 over 2 pi times 50 times my C, 40 times 10 to the power is micro, negative 6, right? So all this is going to give me 79.6 after solving. So once I get my 79.6, this one is simply going to give me 50 plus 79.6. So don't forget, this one is capacitive reactance and it's taking negative of the operator. So minus 79.6 G, right? So ohm. So this is in the rectangular form. In the polar form, we take Z squared equals our 50 squared plus negative 79.6 all squared. So there's not even need bringing the negative. So I have square root of 50 squared plus 79.6, right? This is going to give me 94. So in the polar form, I have 94 being my magnitude, angle, the angle will be tan inverse of 79.6 over 50, and this is going to give me negative 57.87 degrees. So my in polar form 94 angle negative 57.87, and the reason why it's negative because current is now leading the voltage, so it is negative ohm. Thank you for being with me in this video. Please like, you subscribe, then you share.